Boy, that wasn't long for me. Maybe it was long for you. All right, we're going to do Poisson. So before we did our logistic and we're predicting who died. And so now we're going to predict injuries. Again, injuries is a count variable. We are counting the number of times somebody got injured. And at least for this data set, you can't have 2.5 injuries. So it makes sense to do a Poisson. So because I'm introducing a new variable, injuries, I'm going to go ahead and visualize that. And so we have the majority of people getting between 4 and 6 injuries. And then slightly fewer getting between 1 and 3 maybe. The histogram's kind of funny looking, but that's okay. And then we have even fewer people who emerged unscathed. So that's nothing looks funky there. That looks all believable. Looks like it was kind of a brutal battle. Everybody got hurt, but not many people died, so that's good. Now if we look at the Flexplot of it, and I should probably enter here so you can see what's going on. So like before, we were able to do method equals logistic. Now we can do method equals Poisson, and I thought ahead and I decided to jitter it just so you can see how things are happening. And so this is what we got, and it seems to be, in fact, we could probably add a ghost line. Ghost.line equals gray. And so then it'll be easier to compare the lines. So it looks like the lines are pretty parallel for average and little fighting, but they might be different for high minutes fighting. So there's possibility of an interaction there. But for the most part, it looks like the model's doing pretty good, I guess. I mean, it's kind of hard to visualize and interpret visuals when you got discrete data like this, but this seems to be doing pretty good to me. So on average, the more willpower you have, the more injuries you have, which is kind of interesting. Although, and it's possible that it might be the opposite if you've been fighting a long time, and that kind of makes sense too. That if you have a lot of willpower, you're going to fight a long time, and the only thing that'll take you out is to be really severely injured. And so maybe there's a negative relationship that if you're really high in willpower, I don't know, something like that. So now we can model it. Again, we'll do as before, we'll model an interaction there. And so before we did a family equals binomial, now we're going to do family equals Poisson. So if we ran that model and then ran that model, and I'm going to go ahead and move the compare fits over. I mean, it's the same syntax that we've used before. We're just going to start with a Flexplot-like formula, specify our data set, and then specify the full and the reduced models. And then we get this lovely thing. So what we see is that, yeah, they're generating, again, we're looking, let's go ahead and jitter this actually. Jitter equals C0, comma 0.1. Again, that's jittering the y-axis by 0.1. So we see that they are actually kind of generating similar predictions. There are some slight deviations, but they're not massively different. So, and I actually don't remember what I concluded before, so I can't predict what it's going to say, but I think I'm going to be inclined to say that we go with the simpler of the two. Let's see what the model comparison says. It says, let's see. So the p-value favors the reduced, the Bayes factor favors the reduced, AIC favors the reduced, predicted difference. Yes, that's funny that it sometimes happens and it sometimes does not, that it gives you the predicted difference. I wonder why that is. I'll have to look at that. Anyway, so on average, the maximum difference it predicts is 0.3 injuries. So they're actually very similar in their predictions. So I'd say let's go with the reduced model. Why not? And we can go ahead and visualize the final model. And that's what that looks like. And oddly, and I'm just noticing this, those are straight lines, whereas they are bendy lines here. So I don't know why that is. It might be because willpower is on the x-axis and it spans a wide range. I don't know. Anyway, I'll see if it's an error. If it is, then I'll fix it for you. If not, then it's going to be the same. By the way, this data set can be accessed in Flexplot. There's a data set called Avengers in Flexplot, so you can model this right along with me if you want. Anyway, we'll go ahead and do a final visual of the model. That's actually pretty. So that says the longer you fight, the less likely you are to have injuries. And I actually made a note. Wait a minute! And so I first thought this was a mistake because I simulated these data, so maybe I just flipped or forgot to put a negative or whatever. But it actually could make sense that you're likely to be taken out early if you get an injury. So if you fought for 75 minutes, that probably means you have less injuries. So it actually kind of makes sense. And then I'm going to go ahead and look at the estimates. Again, these are in... so this is the multiplicative coefficient. So let me see if I can remember how to interpret this. So that is saying the 0.967 says that every minute you fight, your probability of being injured drops by a factor of 0.967. So that's kind of cool. Again, this is just telling you what the visual is already telling you. It's just putting it in more concrete terms. So I don't know why I have extra ones down there. But so overall, if I were to make conclusions on these data, I would say that our original hypothesis wasn't supported. We don't find evidence that willpower has an effect on the number of injuries you get once we control for minutes fighting, but it does seem that minutes fighting actually has a pretty strong effect. And it's actually kind of negative. The longer you fight, the less injuries you have, which probably means that the causality arrows have been reversed, that you will fight longer because you have fewer injuries. So that is my very quick summary of Poisson regression. The next one, we're going to do gamma regression. So I'll see you then.